Hey guys, we're gonna do two chapter 25 questions, and they're both gonna be kind of moderately difficult. Well, kind of. You know what you're doing. This is from physics. So our first problem: you put the leads from a voltmeter across the terminals of the battery, and the meter reads 12.1 volts. So automatically we are given the voltage of the battery. So we're gonna treat this as the EMF of the battery. We have our EMF is equal to 12.1 volts. You cut off a 20-meter length of wire connected to the battery with an ammeter in a series. In the series with it to measure the currents on the wire. Cool. The ammeter reads 7.3 amps. Cool. Okay. So, okay, cool. So basically, this is what's happening. So we can see that we have a battery. Oh, and for context, it says that the ammeter has a very small resistance and the voltmeter has a very large resistance. So your EMF is equal to 12.1 volts. Cool. I think our EMF is 12.1 volts. Yes, our EMF is 12.1 volts. That is correct. And then it says there's a voltmeter across the terminals of the battery. So the voltmeter has a very large resistance. So we can just essentially treat the voltmeter as a resistor. And the ammeter has a very small resistance. So we can also treat the ammeter as another resistor, but just a smaller value for resistor. So we can say that from the 20 meter, length is equal to 20 meters. We have a battery. This is such a bad drawing. So we have our voltage source. This is going to be your EMF. And then in a series, so across it would be a voltmeter, which is just a resistor. And then in a series, you have our ammeter. So we have a small r, then a big R. This R basically just acts as the battery's internal resistance. So that means that this R is always going to be constant. And then it says that the ammeter reads 7.3 amps. So this ammeter is reading 7.3 amps. And then our next circuits. So we're using the same battery, but this time the ammeter reads 7.3 amps. Oh, this time the ammeter reads 4.5 amps on a 40-meter length of wire. So it's our EMF, same thing here. Then we have our small r, and then R2. But then the L equals 40 meters. And then from 40 meters, so we can just say that L is just equal to 2 times 20 meters. And 20 meters is L. So we can say that, we can actually label these as L2 and then L1. So we say that L1 is L2 is equal to 2 times L1. So that means that our R1 is in relation to this L. So L and R are both related to each other. They're 1 to 1. And the L and the R here are also 1 to 1. So we can just say that our R2 is actually just equal to 2 times R1. Where they're the same in value, but since the length of the wire is changing, we can relate them to each other. So R2 is equal to 2 times R1. And then basically it's asking us to find the resistance from a 1 meter wire. From the same circuit. So if you were to use a 1 meter wire, what would be the resistance? Cool. So since we're in chapter 25, we can use Kirchhoff's loop rule. It's really simple. So it's going to be the voltage difference across each and every single component is going to be equal to 0. Simple. So then we can just go ahead and just write that. That's what we're doing for both circuits. So from the first one, we can go ahead and just do this. Do it this way. When we're coming from the EMF, minus Ri1 minus R1I1 is equal to 0. But this is the internal resistance, and this is the big resistor. And then when we do it this way, actually, I'm going to use a different color for this. And when we do it this way, you can see that barely. I'm going to use purple. Okay, and when you do this way, we are given the same thing, EMF minus Ri2. So our I2, actually, I forgot to give it. I2 is 4.5 amps. And this one, we can't relate it to each other because they're different from, they're basically different. The difference that they make is going to be the length of the wire. So you can't really relate the length of the wire to the currents because the current is related to the resistor, to the resistance, and the resistance is related to the voltage, and we just can't do the same thing we did with the resistor for the amps, for the current. E minus Ri2 minus R2I2 equals 0. Where R2 is basically just 2R1, so we could go ahead and just rewrite 2R1I2. But we can see that both of these have Ri's. R1s. Both of them have R1s. So then we have to either find the EMF and plug it into here since they share the same EMF, or find the value of the small r and plug it into here, and then solve that way. Since we don't have the value of the small r, I would say that we should write this in terms of the EMF and our I's. So our EMF and our currents and our resistor. So we can go ahead and just solve R. Where R, we're just moving it to the other side. E minus R1I1 over I1. Just remember that. So we can go ahead and just rewrite this. We can go ahead and just do EMF minus, we have an EMF minus R1I1 over I1 multiplied by I2 minus 2 R1 I2 is equal to 0. Cool. And then we're gonna go ahead and just solve this. And then our final answer should be solving for R1 here. So whatever R1 is going to be equals to will be our answer. Okay, cool. So we can go ahead and just isolate. Actually, we can go ahead and just distribute this I2 here. Yeah, we're gonna go ahead and just distribute the I2 real quick. So this is going to be E. So the EMF minus, we have our EMF I2 over I1 minus RI1 over I2 minus 2 RII2 equals 0. Or actually, maybe it's better. I think it's better algebraically to do it this way. EI2 minus R1. Actually, I1 disappears if we solve for this. Yeah, we're just gonna do it this way. EMF I2 over I1, and then I1 just goes away over here. So it's I1, I2 I actually don't have an I1 this week. So it's going to be R1, I2 minus 2, R1, I2, 0. Cool. So now we can see that we have a minus. A minus would be a plus. So it's going to be EMF minus this. It's going to be plus this minus this. Does that make sense? We have EMF. This going to be a minus EI2 over I1 plus R1 I2 minus 2 R1 I2 0. These would just give minus R1 I2. And we have our EMFs. We can actually just move this to the other side, right? So then we can go ahead and just rewrite this whole thing. I'm gonna go ahead and just erase this. We can write, we can actually just move this to the other side. Cool. So we have R1 I2 is equal to EMF minus EI2 over I1. And then we have an I2 here. So that we can go ahead and just divide both sides, or yeah, we can divide both sides by I2. And this would give us R1 is equal to EMF over I2 minus EMF over I1. And then we can actually just take out the EMF. 1 over I2 minus 1 over I1. Cool. So plugging into this calculator with our known values, we can just eventually do R1 is equal to 12.1 volts. And then 1 over I2 is 4.5 amps minus I1, 7.3 amps. Let's see what we get. 12.1, 1 over 4.5 minus 1 over 7. We get. And then we are getting the R1 is equals to 1.03 ohms. But this isn't the resistance on the 1 meter wire. Our ultimate goal is to find the resistance on the 1 meter wire. So to find the resistance on the 1 meter wire, this is the resistance for the 20 meters. So we're going to have to divide this by 20 to get the resistance on the 1 meter wire, basically. Okay, sorry, I was just double checking my answers. So we have, we're going to use a different color again. This is on a 20 meter wire. So for a 1 meter wire, so like how we did it over here, we have for 40 meters is 2 times R1. It's because the wire is twice as much as the one we used there. So we're just gonna go ahead and do the reciprocal for 1 meter wire. If this is for a 20 meter wire, we're gonna go ahead and just divide by 20 to find a 1 meter wire. So we're gonna go ahead and just, since R is equals 1.03 ohm on a 20 meters, right? Divide that by 20 should give us the 1 meter wire. So our final answer should be 1.03 divided by 20. 0.515 volt. And the second question will be on the next video.